All right. Hello and welcome to the next episode of 3D and 30. What's fueling launchers race to space? So 3D and 30 is Velo3D's YouTube and LinkedIn live channel. We have a new topic about every 2 weeks, but our schedule does shift around. So make sure that you follow Velo3D to get the latest information. On our show today, we're talking about space, obviously, and the growing infrastructure to both get there and then once there, to be able to move into the proper location or orbit to perform the job. And in space, I think of this as there are growing parallels to terrestrial distribution. For example, on the ground or maybe sea, you might have a cargo vessel delivering from one country to another. Uh, but then once you get there, you need a distribution system to get it to the end user, to get it to the door. And in space, we kind of see a similar dynamic forming where SpaceX now has a launch that has now launched its rideshare program, which provides the cargo vessel, if you will, to get to space. And now Launcher, our guest today, is providing a solution that will get you the last mile. It's kind of like the FedEx of space. Get your vehicle to the correct orbit. And this idea and this business model is not the only one that Launcher is undertaking. So we're going to cover more about what they're doing. But it is helping them get to revenue faster than originally planned. In fact, in about half the time. And for a startup company, this is a very unusual but powerful position to be in. So now it is my honor to introduce our speakers today. Just with a single click, let me introduce Max Haot, founder and CEO of Launcher, and Tim Berry, head of manufacturing. Gentlemen, welcome to the show. How are you doing today?
Great, thanks for having us. Our graphic got swiped, but we'll survive.
Your graphic got swiped. Oh,
yeah.
So you're joining us from what looks like an awesome facility. Can you maybe give us a little bit of background on what's behind you?
Yeah, originally we were founded in New York. That's where I was with my family and other startups when we created Launcher. Then as soon as we could, we had the opportunity to move to California. Obviously the right place for building a rocket company. So right here we're in Hawthorne, a few blocks away from actually SpaceX in our 24,000 square foot facility. We both have offices, additive manufacturing, obviously Velo3D machine, and behind us are CNC machines and EDMR for subtractive manufacturing and finishing parts.
Nice. Just calling in straight from the show floor. I love it. It's awesome. Max, tell us a little bit about your background. I think you have an awesome history.
Yeah, so originally I'm an internet entrepreneur. So I created a company called Livestream about in 2007, which we sold to Vimeo IAC in 2017. And part of the proceed of that and also my free time once that was done was really the start of Launcher in 2017. I also more recently created a video consumer electronic video camera company called Mevo.com, which I ran in parallel during the early days of Launcher. So that's a camera. We've made more than 200,000 of them in manufacturing, and obviously it's hardware and electronics and software together. And I recently sold that business. This was based in New York, or is based in New York, to Logitech, the consumer electronic company. So that sale was in February last year, and so that's when we moved Launcher from New York to California. And at the same time, we also significantly scaled up our team and our roadmap and our infrastructure. So now we have the factory we discussed, but we have also 60 team members in design, manufacturing, and many other skills that are helping us. Today, our focus is Orbiter, as you mentioned, our transfer vehicle flying in October on SpaceX rideshare with many parts, 3D printed with Velo3D. And then in 2024, our launch vehicle from the ground, Launcher Light, which is a unique aspect is that we focus on highest performance propulsion and also scalable propulsion, whereby our first stage is a single E2 engine. And once again, this 10-ton force or 22,000 pound thrust stage combustion closed cycle liquid rocket engine has many parts in the turbo pump 3D printed on Velo3D. So yeah, there are two products, and one of the unique aspects of Launcher is the focus on performance instead of just trying to go as quick as possible. We believe it takes a long time to build rocket engine, 5 to 10 years, or vehicle. And so you may as well make sure you have the most competitive one and use the highest performance technology. And then obviously this tactic, the fact that our third stage of our own rocket is also a transfer vehicle, a scooter you could mention, that gets a ride and is compatible with SpaceX rideshare, That's a unique aspect of launcher. We're the only one that is both building a launcher from the ground and a transfer vehicle. And it really aligns us with our customer, because the first thing we do when a customer comes with a mission, a small satellite or a CubeSat, and wants to get to orbit, the first thing we do is try to get them to the orbit that they need to, using SpaceX rideshare plus the orbiter transfer vehicle to customize the orbit. And that, we believe that nothing can beat the economies of scale of using the very low cost $5,000 a kilogram. Actually just increased 7% for inflation. This price per kilogram is unprecedented in the industry. You have a flights every 3 months to orbit. And so we do everything we can to fly our customer through that. And we only offer our upcoming launch vehicle from the ground, first mission in 2024, if it cannot be achieved with the bus, with the cargo. And at that point, it's at a premium. You can't beat the aggregated large rocket. But if you need to go to a specific orbit at a specific date, there's no choice. You need to go from the ground, and you need to actually shoot the rocket in that direction.
Awesome. You mentioned a lot of different things. We're going to take this next 20 minutes and unpack it all. But you mentioned the growing team, and I wanted to shift it over to Tim here.
I'm Tim Barry. I'm the head of manufacturing here at Launcher. I just recently joined Launcher. I previously worked at SpaceX for the past 9 years prior to joining Launcher. I started as leading the second stage integration team, producing upper stages for the Falcon 9 launch vehicle. Then I moved to Dragon Integration to lead that team, performing final integration of the crew and cargo capsules, starting with the IFA in-flight abort capsule, owning the Demo 2 build all the way through the Crew 3 capsule build. And then I transitioned over to be head of additive manufacturing at SpaceX prior to joining Launcher.
Nice. Well, hopefully you can hear me.
Yeah.
Thumbs up. Okay, good. So Max, you kind of talked a little bit about the industry, and I know a lot of things have been affected, obviously events recently. Where do you see the space industry today? What's the trajectory that it is on?
So, the first data point I like to quote is that there's about 5,000 active satellites in orbit right now. And that number was about half of that 2.5 years ago. So we've, all satellites from all nations that are active have doubled in the last 2 years, primarily due to SpaceX Starlink and also to the small satellite revolution. And so if you look at where it's going, we're not stopping there. This is not a last 2-year anomaly. So firstly, SpaceX Starlink is the largest constellation out there. Very soon, in 1 year, there will be more SpaceX Starlink than any other satellite, so more than 50%. And we don't think that's an anomaly. We think it's the beginning of what's to come. There will be other internet constellation of similar size. We think Starlink is maybe 10 years ahead. There will also be a lot of large constellation for different application. Some already exist for observation, other communication, and so on. Life science, military applications and defense. And so it's just the beginning. And if you look at the industry, we first went to space in 1957, about 60 years ago, with Sputnik, and then obviously the moon landing. And you can think from a lifetime, this is an old industry a long time ago, but if you look on the human scale, it's pretty incredible that we're all alive, just a few seconds on a humanity scale after this really happened. So for us, it's right at the beginning. And if you look at space infrastructure and satellite, the 90s and the early 2000s and sort of mid 2010s were just a flat market with very large satellite, very expensive one. And then, you can see the explosive growth in the last 2 years. That's just the beginning of what's to come. So we believe that we'll see, hundreds of thousands, not just 5,000 active satellite on orbit in the next decade. And we'll see also a lot of application. A lot of the people launching satellite are competing with existing traditional large satellite application. But in the same way that with the internet, you couldn't predict in the late 90s what we use the internet for today. We think you'll see the same thing with satellite infrastructure. So in 10 years, there'll also be new application, us on this call and our viewers cannot think of today. And this will be through the trial and error of entrepreneurs. The barrier of entry are low enough that entrepreneurs can raise money and launch a small satellite constellation and innovate.
you kind of mentioned two vehicles, the launcher light, which I think we have a picture of here, and then the orbiter
Mhm.
vehicle. Um, now, how are you looking at these two in terms of prioritization, and what affects your decision making in them?
So from a business point of view, they are to some extent two different products, although they do the same thing. They deliver payload to a given orbit. But from a technology and development point of view, Orbiter is the third stage of Launch Alike. So we were always going to build Orbiter, and what we did is we fast tracked it and we made it compatible with SpaceX rideshare. So originally, the third stage was going to be the last thing we developed, and with the opportunity that SpaceX created when they launched the rideshare program late 2019, early 2020, we realized that we could make it compatible and we could offer our customers the best of both worlds using the same product. So from a development point of view, we brought Orbiter right at the front. We're also developing in parallel the structures, the fairing, and most importantly, the engine for Launch Allied for our flight in 2024. But 80% of the organization, manufacturing capability, testing people here are all focused on building our first orbiter, which is flying in October this year. So it's a very exciting year where not
Nice.
only we bring in customers, but we're also reaching orbit as a startup.
And so, I mean, you mentioned fast tracking on the product side, and I could imagine the implications that's going to have in manufacturing. So, Tim, what are you experiencing with when you make a change like that on the manufacturing front, and how have you been able to navigate that?
Yeah, so I think the additive technology, and particularly like the Velo Sapphire, has made it really easy for us to iterate, pivot easily. There's not a lot of expensive tooling. It has a lot of capabilities that enable us to print complex geometries. So I think the priority shifting around, especially with the fact that most of our components are 3D printed, I think it makes it a lot easier on us and makes us more nimble as an organization to be able to shift between the two products. And that's really the benefit of the additive technology and using really highly capable print platforms.
Now, I think, and we talked a little bit before, obviously, on a Velo Virtual a couple months ago. We talked about this the E2 liquid oxygen pump, and that's what we're showing here. Can you walk us through kind of what we're seeing in this image?
So for the Launch Allied vehicle, we have a single E2 liquid rocket engine, and that engine has really two key components. If you remove avionics, sensors, and valve, it has a turbo pump, single shaft turbo pump, liquid oxygen RP1, and it has a combustion chamber and an injector. So right there, you're looking at the turbo pump, the liquid oxygen turbo pump, and the turbine, soon to be added with a fuel pump on the left side of this flange you see. And so our relationship with Velo started. We've been doing 3D printing first without our own machine, but with service bureau and partners since we started in 2017. A lot of the startups that are building launch vehicle or rocket engine, or none of them would be around if it wasn't for 3D printing, lowering the barrier of entry for combustion chambers and injector, and making sure we don't have to do very complicated and expensive tooling for brazing to access this technology. And so we've been doing combustion chambers and injector using other competing platform. And then came the time to build our first turbo pump for testing at NASA with a Space Force SBIR grant. Our unique approach is we've actually licensed a space-proven turbo pump for stage combustion, which is the hardest kind of engine cycle from Ukraine and the ex-Soviet Union. And we licensed the drawing. This design has already gone 80 times to orbit as part of the Zenith launcher. And then we mapped it to US material and obviously used 3D printing, modified the flow path, and went to test it successfully. So one of the components that we can't show due to ITAR inside this turbo pump is the shrouded impeller. And I'm sure a lot of people have seen what it looks like. And the shrouded impeller is very hard to manufacture because it has 0-degree angle. It's also an extreme part. It's at in our pump, it's at 30,000 RPM, more than 300 bar of pressure, outlet pressure, and it's with liquid oxygen as a working medium. Which, if you have any contact between the rotor and the stator, goodbye, your pump disappear. So we could not, with competing platform, manufacture that part, and that this was late 2019, early 2020, and we had already heard about what Velo was doing as early as 2017-19 when your website just had a logo. and we sort of were hearing rumors of what was going on in California with Velo. But at that time, you did have a website, and we did speak to some of the team members, now that we are drawing. And the team at Velo took the challenge, and we ended up with a finished part that we tested successfully and met and exceeded all of our performance objective with 64% of efficiency. And so some of the parts I can show. So for example, this is, we can show the outside, not the inside of these parts, but this is the output of this liquid oxygen pump, and it's printed in Inconel on a Velo Sapphire without any support, and then machined. And then this is a separate part. So this is again for the 10-ton force, 22,000 pound thrust, liquid rocket engine, highest performance, lowest cost is our objective. This is the inlet, also printed on Velo 3D, in aluminium in this case, given that the low pressure. So the launch vehicle tank comes in here, and then the outlet was right underneath. So that was the beginning of our relationship, and then we moved, as we covered, to California, and we started to build our CNC capability, and was the time to get our first printer. We reached a deal with Velo 3D to get an Inconel Sapphire, which was our first printer last summer. It's on our floor here. And so that gave us the capability to start doing this in-house. At first, we were able to work with a great network of service provider. Protolabs and Stratasys were the partners that helped us build the first pump. But now we want to accelerate and iterate, and so we bought the tool and started building our team and making our own parts in this factory.
And now you're fast tracking to the orbiter vehicle. Kind of have that here.
Mm-hmm.
Yeah.
Go for it.
Yeah.
So
I was just saying, if you could give us a rundown similar to what you did on the pump there on the parts that you're printing.
So as a modern, space and rocket company, there are a few, really important approach that we must take. So the first one is for Orbiter to get the lowest cost in the industry for the highest capability, propulsive capability. Our focus is to have as much in-house design on as many components. If you start to buy a separation ring, a propulsion system, structures, avionics, solar panel from third party, and you integrate them, your cost basis is going to be 10 times or more higher than what we are doing. So to be competitive, we believe not only vertical integration but in-house design is the key. And so for Orbiter, when it came to design it, take it from this render to what we will fly in October, which we haven't revealed yet. I think it looks a lot better. We basically also applied another principle that's very important to manufacturing or rocket startup, which is designing for the tools you have. Every time we send a part out of house to do a process, it hurts us, right? We go from being able to design an engine, print it, test it within a week to within maybe 2 or 3 months if we have a third party in the supply chain. And so for Orbiter, for example, the engine we built it. So this is a prototype with the extension nozzle. You can see on our website or on our Twitter at launcher, we successfully tested this piece, which is cooled with nitrous oxide. This is a nitrous oxide ethane engine, and this is the injector, which I guess you'll show a picture. And so we were able to design it for the Sapphire printer in Inconel, successfully tested. So these are the final design. These are the injector that are pressure fitted on top of this, and obviously machined and printed on the Sapphire. And then another big challenge if you're doing propulsion is tanks. Tanks, if you go out in the industry and you just shop for space graded tank of 3,000 psi burst pressure, 1,000 psi working pressure, you probably will be given lead time anywhere near 8 months to 2 years, especially if they are custom, which obviously is not possible for us. So once again, we took the approach of designing to the tools we had, and we started experimenting with these tanks. So there are 8 of them, 22-liter tank, which is actually exactly match the Velo 3D or maximize the Velo 3D Sapphire volume. And at first, we did these tanks in Inconel because that's the tool we had, and it performed pretty well. But then we thought we could optimize it and anyway, we needed more printing capacity if we were able to do titanium. And once again, we knock on the door at Velo and figured out a purchase deal for a second printer. We have a third one. We have also a competing one here, but we have two Velo 3D. And we switched. We had done all the development and all the design in Inconel, and then we received the titanium printer and put the same model in it. We obviously changed a little bit the thickness, given the material properties of titanium, and obviously we can have a lighter tank and higher performance, pressure to weight or mass saving. And we printed it, and now that's how we make our tank. So it takes us right now a little bit less than a week per tank, which is too slow, but there's already a long list of improvement that Tim and his team and also Velo 3D have on the R&D piece. So that's the other piece, is that not only for every tank we can change a little bit the design to add a mount or do something, move a port. It's very easy, and we get a new tank a week later. But also there are ways to optimize, I guess, lasing strategies and layer thickness that gives us the potentially the hope for getting to 4 days or something like that on this printer. Obviously, some of the newer Velo printer with more lasers would be a lot faster and even bigger tank. So that's sort of our approach. And so Orbiter, we have structures, titanium structures are using Velo. Secondary structures like bracket and all of that, we're doing also in Velo in titanium. Tanks, 8 of them, which is the biggest part of Orbiter, is done on the Velo, and then the combustion chamber and injector. And then everything else is obviously electronics, avionics, we do in-house. Separation ring or more traditional aluminum CNC mill. There's a big plate at the top. That's CNC. But what's important is also all of these other processes, not just a printer, are right here. And the clean room is being built here. In May, we'll be integrating. So you can see what we're trying to do is that to vertically integrate everything so that it's the lowest cost, but also we can build them very quickly, in 2 months from end to end or something like that.
Okay. We do have a couple questions regarding some of the things you just mentioned there. One of the questions is, you mentioned the fuel tank is the size of the Sapphire, and I also mentioned kind of about the XC. So this comes in from a LinkedIn user. Does Launcher have any plans to utilize the new Sapphire XC to print larger hardware?
We're not ready to announce anything, but we're very interested to print larger things with more lasers.
Yes.
I'll leave it at that.
That's what we'll say. Yeah.
All right, fair enough. And then Lucas has a question about maybe more on the manufacturing side. Do you need to hip hot isostatic press the impellers or inducer after printing?
Yeah, hipping serves a dual purpose, as a lot of people are aware of. Homogenizing the material, especially from printing, which oftentimes versus casting can introduce a lot of porosity into the parts. And then additionally, the secondary function is stress relief function. So rather than having like an independent stress relief cycle and then going into heat treating, we hip the parts to get the benefit of homogenization in addition to the stress relief all in one go.
And one of the advantages to be here, like hipping machine is what, $1 million, something like
10,
that.
big
10
ones.
big ones. Yeah. And so that's one of the tools in our supply chain. We have EDMR, we have the printer, with CNC, where we don't have it yet. But being in the South Bay area right here, as you can imagine, we have partners where with about a day and a half, maybe turnaround, we can in the morning get the part, and then a day and a half, it's back here for EDMR. So, but yeah, we do hip. Sometimes we try not to do it. So, for example, our combustion chamber, right now we're getting away without it, but we might still do it. So it makes sense to sometimes try without, but the precision and obviously the stress relief is really problematic, and the material quality is not as good. So so we think it's worth doing.
It becomes a lot more important as well once you start increasing your layer thickness, because you do introduce a lot more argon porosity into the parts. So hipping takes on extra importance once you're printing with thicker, maybe 80 or 100 micron layers.
There is another question here regarding the material change. You mentioned you went from Inconel to the aluminum.
Mm-hmm.
And how difficult was it to change material, and did that have any introduce any design challenges?
So one of the uniqueness obviously of I should say that there is no structure inside. So one of the uniqueness of what the Velo can do is this like zero overhang top of the tank. On a traditional printer, there would either be structures inside the tank, or there would be more of a 45-degree cone, which would have a lot less fluid density for the size of the printer. And so for this, we, obviously as you get to zero overhang, it's not the exact same material quality and properties as you on 90-degree, but it's definitely good enough. And so with titanium, what we liked is we were able to increase the thickness of the wall while decreasing the mass. So we went from 1.4 millimeter to maybe 4 millimeter, I think, from memory on the titanium tank, and reduce mass a little bit. And so that makes it easier to print. More wall thickness makes it easier to print at high quality these type of geometry. So, but other than that, everything was exactly the same. So just the thickness changed, the mass was lower, and the chance that the 0 degree succeed, at the right quality for burst pressure increased given the 4 millimeter.
And Tim, you have mentioned a lot of different machines on site. Some parts you're CNC machining, some parts you're printing. What helps you or guides you in making your decision on what platform to use for the parts?
Sure. So as Max had said before, it's all about cost and production rate. So we look at how much how much of the asset time and utilization we're eating up doing specific components, the associated costs for the materials, downstream processing. A lot of more legacy processes like casting have a high tooling investment, and also require a lot of labor, and it's still a very manual process. So just looking at the overall, like how labor intensive the process is, how many different components we can consolidate together, which obviously 3D printing is great for, the density of complexity that you get with that. And then, overall just weighing the cost and time trade-offs for each of the production methods.
And there's also geometry. So for example, right now, originally we were printing in copper or E2 injector, and right now that's another part we print on Velo, because it's a coaxial swirl injector, and there are very small tangential orifice for the fuel, and these are vertical, so they're 0 degree overhang. And so with Velo, we were able to print them without having teardrop shape, and also to print them as circular orifice. And we were also able to replicate it and have the same flow between different prints, which is what's important, and also between different elements. There's probably 200 elements or something in that order of magnitude there. So also the choice would be, okay, we have these assets and this design challenge, and then we would pick the right printer, and sometimes even compromise on material. We'd rather that to be copper, but we have Inconel, and so we make it work for the tools we have.
Yeah, I think also Velo allows us oftentimes to not have to completely change our design to make it fit the printer. Oftentimes it can do the standard geometries that we planned in the most optimized design that we have, and we don't have to make a lot of compromises when it comes to the final design of the parts to fit the printer.
Very cool. And you mentioned kind of keeping things in-house. What guides your decision on keeping systems in-house versus using a supply chain approach?
I mean, we want to have as many of our tools in-house, and then the decision is what we don't bring is really investment and soon space. We didn't have space for a while, but now we're getting a bit busy.
Yeah.
But it's investment and versus the service out there. So for example, HIP is an example where it's a high investment, and there are really great service locally. So we're unlikely to in-house it for a very long time. But there are other things we do still today that, for another example is laser cutting or water jetting. There's so much supply chain out there that, it's really not enough of an issue in cost or time that we plan to do it. But then, there are other things that are on our list, for example, heat treatment, if there's something, vacuum heat treatment, we don't have it, and we'd like to have one. And it's just a matter of when, with our company's funding profile and our priorities for resource, staff, equipment, when we can do it. So we have a target list of tools, and we're trying to get them as soon as we can so we can speed up.
Okay. We have a couple questions here that have already come in, so I think we'll get to those and then we'll wrap up. We are at 30 minutes right now. One of the questions coming from Greg is regarding quality assurance, quality control. What do you have in place for that today?
Yeah, so we do for parts that come off the printers and prior to machining and then after machining as well. We do a lot of dimensional inspections, making sure that the tolerances are correct, making sure that our programs that we run in our CNCs produced the correct hardware. We also do a lot of boroscope inspections and patching inspections for the printed parts to make sure that we've gotten all the powder out, obviously before it goes to hip. So that we don't end up with any blocked channels. Additionally, we do visual inspections of the surfaces of the parts to make sure we don't have any, not too much cracking, porosity. And then finally, we do material testing on each of the components that we print to make sure that the as printed tensile strength is what we expected.
Yeah, so this tank obviously has to fly to orbit and be safe. So we're going through a full qualification process, which obviously includes coupon with every print, fracture testing, burst testing, cycle testing, vibe and shock testing, and then eventually, hopefully, approval by the range at basically Kennedy, the Space Force range, to let us fly and to fill propellant in this tank. Before we made to launch to SpaceX Falcon 9.
Yeah. In order to find the best material properties and parameter sets, we do like a DOE and then a visual down selection, and then from there we'll do an additional DOE and then send those parts out for fatigue testing and other material testing to make sure that we have a good parameter set that we're happy with.
We've gotten asked before about pressure testing for vessels like this. Have you done any pressure testing on this? And if so, can you reveal any of the results?
There's the goal. So the propellant in these tanks, in the titanium tank you saw, is gas stored as liquid. It's either nitrous oxide or ethane, which have similar pressure at the similar temperature. So it's not like pressurized with helium; it's self-pressurized. And so if you increase the temperature, it increases pressure, but the working pressure averaged about 900 psi. Then on top of that, we have to have what's called a MEOP, which takes other factors into consideration. So it's about 1,000 psi MEOP, and then the range requires a factor of safety on top of that, which is about 2. So it's about 2,000 psi. But we want margins on margins, right? Because we could have a variance, and we also want to be extra safe on our first flight. So right now, the burst performance of that tank is 3,000 psi. That's where we're at for about 5 kilograms. And probably on flight 2 or 3 of Orbiter in 2023, we'll start taking down the wall thickness to get closer to an aggressive design, closer to the 2,000 psi burst. And we think we probably can get, top of my head, about 3 kilogram total, maybe 3.5. So there's conservatism in the first design so that we don't run into, concerns. There's plenty of margin, but then thanks to 3D printing, it's very easy to basically get more aggressive and then test that.
And there's a question: do you buy a printer for each metal currently, like a separate printer for each separate metal?
Yes. So currently, for each of the materials that we print, we have a separate printer for it. I have in the past changed materials between printers, which with Velo is relatively quick and painless. And so if we do need to change materials, typically it's not easy to switch back and forth every day. But if you decide down the line that you want to change over your printer to another material, Velo is super helpful with it, and it's a relatively straightforward process.
But to play devil's advocate, Velo has many advantages to competing printers, but there is a requirement to sort of stick with one material per tool, and sometimes you can change it with a process. Other competing products, we have another printer where we regularly switch between copper and aluminium without much work or support. That's something hopefully we'll see in future Velo printer. But right now in previous experience, Tim has done it, but we at Launcher have 2 tools, one dedicated to Inconel, one dedicated to titanium for Velo.
And there's a question here: how long does it take to qualify new material on a Velo 3D machine? I can take that, or if you want to
Well,
answer that.
one of the point, one of the criticisms sometimes of the Velo system is that it's very closed, but on the other side is that it's very the positive side, it's very turnkey, and especially for a multi-laser system, we have two 1,000 watt lasers. There are new systems from Velo with 8 of them. What we hear from the traditional open system, where you can do your full own parameters and obviously you fully control the laser path. It's a lot of concern with laser overlap and strategies, and really, us having to think about that. With the Velo system, even though it's a little bit more closed, we don't have to think about material qualification, and we don't have to think about how to handle the different lasers, right?
Yeah,
correct.
Comes with a great base parameter set.
And maybe for a service vendor that wants to create a lot of intellectual property, that's not great. But for launcher as an end user, this we don't want to develop parameters unless we have to. And right now, there's no reason to with the needs we have with Velo. So it's not really an issue for us.
Yeah, I think Velo takes the pressure off of at least the base parameter set, and it allows you to focus more on iteration and improving for your specific use case.
All right. Well, I think you handled that pretty well. So I definitely want to be sensitive to time. We're at 37 minutes here once I finish the sentence. So if I could get some closing thoughts from you, Tim, maybe kick us off.
Yeah, just overall, in my previous experience and my experience here thus far at Launcher as well, it's been amazing working with Velo. I think the applications engineers, platform engineers, service in general, field service engineers are unmatched in my experience in the industry. So we've really absolutely enjoyed the service that we get with Velo and the capabilities that the machine provides to help fuel our race to space.
Yeah, I think it's the same. We had we're getting a lot of software upgrades, a lot of support from the application engineer at Velo, which is, it feels it's not static, it's moving very quickly. The flow software and other things. We also get once in a while hardware upgrade, and one of the ones I really liked, we had a recorder upgrade, and the technician took away parts from the machine. I thought that was a really interesting improvement, and for improving the recorder speed. And then, I think we've touched a lot on some of the differentiator in what it can do in terms of geometry. But here, if we obviously lucky we're in a geography and nearby, very large installs of Velo 3D machines. But the service is just incredible. I don't know if maybe there are people in Europe here. I know you have a first printer in Europe, and the other geographies in the United States might not get the same service, but it shows us the culture of Velo. And for here, it's just incredible. Like, 10 minutes after a text message, maybe within an hour, we have a technician with parts showing up. No ticket, no phone call to a call center, just direct relationship.
Yeah.
Maybe not scalable to everywhere, but we really appreciate it, and it makes a big difference.
Yeah, I know that's something Benny takes very seriously, scaling up our service and support. So the intent is to have everybody basically experience what you're describing. And in Europe and Australia and Japan and Korea and everywhere, we've got printers all throughout the U.S. too. So,
awesome.
Well, I think we've used up 40 minutes here. I think this is an awesome session. I learned a lot. I really had a lot of fun. Thank you, audience, for staying with us. Great comments. I'd love to see the interaction between the audience and our speakers. And and I can't forget, happy St. Patrick's Day for everyone. Hopefully you're wearing green or you get pissed. There you go. All right.
Great. Thanks, everyone.
That is a wrap. Thank you.
Yeah, thanks, guys.